Alright, how you doing? My name is Rivet, and I'm going to be reporting on time constant for the boiling water experiment. So the objective of this experiment was to record the transient response of a K-type thermocouple submerged in boiling water and then removed from it, and then determine experimentally the thermal time constant. One assumption we made here was that lump capacitance was valid. This is that heat will conduct quicker through the object than across the boundaries. And then from there, our governing equation is this energy balance, which is the transient temperature response on the left, and on the right is the convection. And then that equation gets massaged to where you determine the time is equal to the negative of the time constant times the natural log of the temperature change. So the equipment we used in this experiment was pretty basic. On the left is a 500 milliliter flask, half filled with water, a hot plate, a computer with a data acquisition module, and then a type K thermocouple shown here that was sheathed in stainless steel. So for this experiment, basically we put the water in the flask, turned the hot plate on high, got the water boiling, and then we started the data acquisition, submerged the thermocouple into the water, and then left it there until the temperature stabilized, removed it, wiped it off with a paper towel, and then set it down and waited until it returned back to ambient temperature. So the raw data collected is this. As you see on the left where it starts out, we started around 22 degrees C, and then it went up to a little over 100, hung there until we saw that it was stable, and then removed the thermocouple, wiped it off, put it down. One thing I noticed when I was looking at the data is this point right here. I'm not quite sure what happened there. The temperature dipped and then came back up, and then after that it pretty much just declined. So the first thing I did when analyzing the data was normalize it. So this is the graph for the insertion of the thermocouple. Start at 1, and as time goes on, it decreases down towards 0. Same type thing happened for removal, except it took a lot longer. It was around 10 minutes, I think, that we had to wait for it to get back to around ambient conditions. For this, our initial temperature was, I think, 100 or 101, whatever it read steadily before we removed it. Then after that, I graphed the log of the normalized temperature versus time. So for insertion, it was this. It declined much slower than the removal. As you can see, the time constant here was 0.605. And then for the removal test, the time constant was 90.1. I'm not quite sure what happened here. I initially thought that all this was due to that hump I just pointed out. Then I realized that's actually happening right here. So I think that's just because the temperature, once it got down to 23, 24, it would really fluctuate. It was kind of going up and down a lot. It wasn't continually going down. So like I said, the time constant I got from this was around 90. The significance of this, so the thermal time constant is used to measure or kind of characterize the thermal responsiveness of the system. In theory, it's affected by these 5 things: the density of the thermocouple material, volume, specific heat of the material, the thermocouple, the convective heat transfer coefficient, and then the surface area of the thermocouple. So the only thing that really changed between insertion and removal was number 4, the convection heat transfer coefficient. So that's what resulted in such a big difference between the two thermal time constants. As you can see again summarized, for insertion was 0.6, and then for removal was around 90. That's that due to convective heat transfer coefficients. The convective heat transfer coefficient for water is greater than that of air, so that's why you had a difference. As far as significance for this, I thought it was significant because from past internship experience, we've used thermocouples to monitor our reactor, and that's kind of like your first line of defense of noticing if you have a runaway reaction. So you don't want to have a big lag between having a temperature spike and then actually seeing the control room for the operator. So having, I guess, a thermocoupler system that's very responsive to changes in temperature will help you run a safe product. So, any questions?
One question. Can you calculate this result theoretically?
Yeah, that's what all those 5 things were. So I didn't put the equation in with what it is, but it's like the tau is equal to, it's like 3 things over 2 of these.
You put one equation at the beginning.
Yeah, I didn't put
Yeah, this.
I think it's, was it rho VC over HA? That's how you can theoretically calculate.
So what is the rho? How gonna